Hello, 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 hello. Hopefully, you can see me and hear me all right. We are live back with one more live stream episode of Baji and Physics covering cosmology. Today, we will talk about the Big Bang as well as sort of leading up to the formation of galaxies and at what point in the universe, in the evolution of the universe, did galaxies start to form? Because it was definitely not at the very beginning, something that we spoke about last night as well. So if you have not been to that live, then I highly recommend also playing that one because this is kind of part two of the live stream from last night. But in the meantime, while I wait for some more people to join, I'm going to put my earrings on. So there's going to be that. And do tell me how you're doing. Hopefully well. And if you're seeing this later on as a video upload, then please do leave a comment. If you see this live, please do tell us in the chat how you're doing and how everything is going. And feel free to like, share, subscribe, give us your comments, give us your chat messages, ask any questions that is pertaining to physics, astronomy, astrophysics, cosmology. For some reason, I almost said chemistry. I used to major in chemistry as well, but these lives are more focused on physics and astronomy, astrophysics, cosmology, which is the last one. Of course, cosmology is the study of the universe, especially from the Big Bang all the way up to the evolution of the universe at the current state now, and things like looking for dark energy or understanding dark energy better and understanding the expansion of the universe better, as well as something like dark matter, understanding the nature of dark matter. Those all kind of fall under cosmology, as also does understanding a large scale structure, which is also something that we touched upon last night. And in the large scale structure formation type of topics is where sort of galaxies come into play. So for a while, we didn't really talk about that because in the very, 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 very beginning of the universe, and we even set forth certain timelines of exactly what I mean by very, very beginning. It could be 300,000 years is still very close to close to the beginning of the universe, given that the universe is around 14 billion years old, or it could be 10 to the minus 43 seconds, which is also towards the beginning. So we kind of started to go into some of these specifics last night. So we will continue from there tonight after I say hi to everybody once people have joined and whatnot. Okay, so thank you very much indeed if you're joining. I'm gonna share the live after I brush my hair here. And I am going to take a moment and share the live as well. So if you're joining, please do say hi and welcome, welcome, welcome. If you say hi in the chat, then I generally will say hi back, especially in the beginning of the live, because I kind of like to welcome everybody to the live and then get started with the topic. So this is the beginning. So if you're saying hi in the chat, this is a great time to do that. And let's see, let me share the live. Also, please do like, share, and subscribe on your end as well, because indeed I will be telling people to do that in the chat. Okay, now I will make sure. So hopefully everything is working. Is the video, audio, everything working? I hope that is the case. And we might just launch into the topic right away. It's 11:45-ish. We are live. I will say to the community post of my channel. Thank you, everybody. If you're seeing this later on as a video upload, I really do appreciate all your thoughts and comments. Any questions, comments, all of that can go in the comments of the video once it gets uploaded. And if you see this later on and we have already kind of started, well, I don't know if you'll hear me say this, but please do rewind, and then you can see the whole thing. Okay. So now how do I yes, okay, I see. Thank you, everybody. Please do say hi in the chat. Okay, so I think I might just get started actually. So I wanted to remind you that we are talking about this book, Astrophysics for People in a Hurry. See, this exact book. It's called Astrophysics for People in a Hurry. So if you're in a hurry today, we will be hopefully adding a lot of value to the live stream here. Because we are going to do a little bit of a book reading along with my own comments. And the author of this book is a very famous person indeed. He is Neil deGrasse Tyson. So he has a number of books. I wanted to mention that Neil deGrasse Tyson has a bunch of books, and I have like 3 of them with me right now. And this is a sort of a popular science book, so it is not going to be as detailed as some of our other lectures or other sorts of discussions that we have had. Sometimes we have even gotten into nitty-gritty of certain general relativity mathematics when we talk about cosmology. And this discussion hopefully kind of complements those types of topics and times when we covered things in more detail and also used this other book. So I wanted to also mention this book, Modern Cosmology by Scott Dodelson, is a reference book that we also use for these topics like the Big Bang Theory, evolution of the universe, expansion of the universe, the total energy density. So I'm just kind of saying some of the terms that in order to jog your memory, if you kind of catch these lives regularly, then these will be helpful. So energy density of the universe, the matter density, the total energy density, those types of things we have talked about. And we saw how 70% of the critical energy density contribution comes from dark energy, and 30% comes from the total matter density, of which only about 5% is the ordinary matter and 25% is the dark matter. So those types of things. We talked about cosmic ingredients, if you remember. So this topic is actually what we kind of talk about here as well. Hello, I see user random alphabet saying yay. Hello, user. Hello, random alphabet. Excuse me. As soon as you joined, I had to sneeze. So excuse me, and thank you so much for being here. Could you please like, share, and subscribe to this live and this channel? Thank you so much indeed. So user random alphabet. I don't know exactly who you are. Are you the... one of my... Oh, yes, you're B. Got it. So user random alphabet is actually B, our old friend on this channel. So welcome, B. Snokomui. Hello, Snokomui. Snokomui is saying buttercup. Hello, buttercup. Hello, Snokomui. How are you doing? B is saying bless you. Thank you. Brady Holmes, Sherlock Holmes. I love Sherlock Holmes. So Brady Holmes, I like your last name. You are so beautiful. I could hear you talk all day. Thank you so much. Please do like, share, subscribe so that you can hear me talk all day. And in fact, you should hear me talk all day. You should play all my episodes under the live tab of this channel. There are many. I've been doing these lives now for over a year. And so we have many, many, many episodes that we have kind of talked about these exact topics, physics, astronomy, cosmology. So you are welcome to hear all of them. Just keep them playing in the background as you do your other work. You go to the bathroom, you take a shower, you go to your office. And also please tell all your coworkers, your family members, your neighbors, your sisters, brothers, and everyone about this channel. Please, I appreciate it. Thank you. So B is saying the user, yes, the username used to be B. Brady Holmes is saying I will. Oh, thank you so much. You know, you guys have made my day today by being here on this live stream. Please do like, share, and subscribe. Please like the live. Can we get as many likes as there are people, which is both very small right now. Anyways, so the Neil deGrasse Tyson this is a question answer thingy thing that YouTube is asking me to start. I suppose it could be something of value maybe to people. So let me do that. There, it's done. So Neil deGrasse Tyson provides a very easy to read text on some of these same topics. So what I've been trying to say is that we have covered cosmology topics in quite a bit of detail in the past, especially if you remember certain discussions like the cosmic ingredients. Remember, we talked about the 5 cosmic ingredients of the universe, like literally all of the universe pretty much has just dark energy, dark matter, photons, neutrinos, and baryons, remember? And pretty much in the context of cosmology, baryons kind of just fell or kind of captured all the ordinary matter, and which included electrons. But technically speaking, electrons are actually not baryons, they are leptons. And in the context of more particle physics discussion, we would be more careful about that, okay? So just a few notes here about certain terminology. Sometimes the terminology of cosmology is a little bit different than the terminology of particle physics, and you might have to pay attention to what these different types of physicists mean, okay? So particle physics is where, of course, we would be more careful about naming and being specific about the particles. So let me say the same thing in another way now, which is that pretty much when it comes to cosmic ingredients, what is the universe made of? Now we know that in terms of ordinary matter, really most abundant element in the universe is hydrogen. So now hydrogen is just a proton. If you consider it as just the normal hydrogen nucleus is just a proton. Now I know that there are some isotopes of hydrogen that we can also talk about, and those are also kind of important in the evolution of the universe, but just the hydrogen is only just proton. And so that proton is made up of quarks. And we talked about it, and quarks are a fundamental type of particle. So you can see how there are some details here. So in terms of the particle physics, that would be quarks, right? It's that hydrogen nucleus is quarks. A couple different types of quarks make up our protons and neutrons. In the quark family, however, there are other quarks as well. But the most common ones that we know and love are the ones that make up the protons and neutrons of our regular elements. So in terms of ordinary matter, pretty much we are now considering basically the quarks, right? In terms of what's in the nucleus. And then if you also want to include electrons in the picture, because sometimes we include them depending on if you are at an energy scale which would support atoms, and sometimes we don't include them. For example, during Big Bang nucleosynthesis time, we wouldn't really include electrons in the same discussion as these nuclei, because, or we would, they can be in the same discussion, it's just that the nuclei and the electrons are probably not together. They're not together, okay? Because it takes a certain amount of cooling for an atom, a neutral atom, to exist. So electrons can sometimes be kind of separate from the picture when we consider nuclear physics, nucleosynthesis, Big Bang nucleosynthesis, and the conditions around the Big Bang. Okay, so these are just things that I wanted to mention so that you don't get it confused. We are not talking about, we're not always, that is, talking about neutral atoms. We do actually mean nuclei, and we might even mean more like the quarks, because those are the more fundamental particle, and depending on which energy regime you're in, we will either think of them as quarks or nuclei, or maybe even neutral atoms. But different conditions are required by each type of thing. Okay. So, so that's some more detail on the terminology, because when we start reading, you will see different authors kind of mention these things differently, and it could be a little confusing. So, in terms of the cosmic ingredients, once again, so I was breaking down for you a little bit about the ordinary matter, which is just you and me, our elements that we know and love from the periodic table, the atoms, the nucleus within the atom, the protons and neutrons, in other words, and those are actually made of quarks. And in a neutral atom, you would even have electron, one or more. Then, in terms of cosmology, however, you have to kind of zoom out and think of the cosmos as a whole. So in that picture, you don't just have these elements and ordinary matter that you and I are made of, but you have more of the universe to consider, and you have the cosmic ingredients. And in terms of the cosmic ingredients, we basically club all of these things that I just talked about with the ordinary matter as baryons, even though technically baryons are the just the nuclei and the different types of I would probably just lump together all the quarks under baryons. But in this discussion by Scott Dodelson, I'm just going to blame him. He also clubs together the electrons under that. So then we have ordinary matter, which cosmologists call baryons. We have photons, which is of course light. We have neutrinos, which is actually a type of lepton. And we have dark matter, and we have dark energy. So those five things. So those five things, those five cosmic ingredients actually encompass the entire universe, okay? What is in all of the universe. So not just ordinary matter, not just the elements, not just us and what we're made of, but all of the things, okay? So keep that in mind as we go forth, and also keep in mind that different authors, because we reference different writers of these topics, different scientists, and depending on what kind of terminology they like, it might be a little different, okay? So Modern Cosmology by Scott Dodelson is quite a detailed and dense book, and we have covered these topics, some of these topics from there, especially in terms of understanding the expansion, some general relativity, dark matter and its role to some extent, the CMB, cosmic microwave background radiation, as well as we have talked about Big Bang nucleosynthesis, especially from that book, which I think is very valuable conversations that we have had in the past. Now we're looking at this book, which is a popular science book. So it's not going to be as difficult, it's not going to be as detailed or dense, but it is rather well written. And Neil deGrasse Tyson is, of course, very well known for these topics. So we are referencing this, and we will keep on going. So last night, this is part 2 of this first chapter that we are looking at. And last night, we kind of talked about the Big Bang, and very shortly after the Big Bang, and I will define what that means shortly, that is. And we had not quite started on the galaxies yet, okay? So once again, after I sip this, give me a second. So once again, let me just repeat myself that let me just repeat myself that the way we see the universe now, as in the current state of the universe, with all the galaxies, with us in it, with the Milky Way, the other galaxies, lots and lots of galaxies. This is not how, this is not what we had right after the Big Bang, okay? And of course, right after is something that should be defined. But pretty much, the universe has evolved to this state that we see now, and that's taken 14 billion years. So don't think that the Big Bang directly created the galaxies, okay? Because I think that was a confusion that we saw last night with somebody who might have had trouble believing that the galaxies somehow come from the Big Bang. Well, they do, but after some other things happen first. So the galaxies, the way we are right now, the current state of the universe, once again, this is the 14 billion year old universe, okay? The universe was at one point just a little bit more than 0 seconds old. Very, very small time indeed is what we talked about last night. Like we basically talked about, let me give you the range. We talked about the interval between t equal to 0. So at the Big Bang, t equal to 0, that is the t equal to 0 when the universe got started, plus from there to t equal to minus 43 seconds. So you understand this is quite a small number. We call this the Planck era. Planck is known for his small numbers, I suppose. And this interval of time, t equal to 0 up to t equal to minus 43 seconds, is what we mentioned about last night. So we really are kind of defining out how small and how young the universe is with those with those very small numbers. So at that point, there were no galaxies. Let me just clarify once and for all. I hope you know that there were no galaxies at that point, okay? Galaxies are a much more mature state of the universe. Like think about the universe as a little baby that was born at this event called the Big Bang. And by the way, the Big Bang is most likely sort of a misnomer in the sense that it's probably neither big, because as you can see, the universe was very tiny at that time. We will talk about the length scale too. And it was probably not a bang. There was probably not an explosion. But also, I should mention that the Big Bang is a singularity. It is a mathematically, it's a singularity, at least in classical physics, in general relativity. As far as I know, I mean, if I'm wrong, please do correct me. But in general relativity or in classical physics, where we of course take into account the speed of light and relativistic nature of all that, where we consider relativity is still classical physics as opposed to quantum mechanics. That physics has sort of this, I would say, defect, where we have this singularity at the Big Bang. We don't really mathematically, not really able to explain the exact moment of the Big Bang, but shortly after, okay? And the same thing as in a singularity is what's inside a black hole as well. So there's a couple of singularities or not so comfortable mathematical positions in classical physics.